Hi everyone. This video is going to be about using F-tool to check the results from your beam deflection equations and how you can use F-tool in a very efficient way to make sure everything works out and then you're doing the right thing in your case. So we're going to be doing this example, so the example 5 that is supposed to be the last video we watched. So the first thing I'm going to do is to take this structure and put it in F-tool as fast as I can. So if I take, for example, that point A is at coordinate 0, 0, then I need to add 1, then 2, then 1, then 1, then 1, and then I'll get to a point B that is at coordinates 6 and 0. So if I go here on F-tool, turn on keyboard modes and turn on the nodes, if I start at 0, 0, I can add 1, then 2, so I'll get to 3, then 4, then 5, and at the end, get to our point 6, 0, that should be B. So if I press now here the little globe, I can zoom out, and then turning off the keyboard modes, I can draw my structure. So the trick of using F-tool to verify the equation that you can see here at the bottom is, first thing is to make sure I set up EI in a very smart way. So the way you do that is, first you open F-tool, you go on to the units and number formatting, and you press here the kilonewton meter. This will have an advantage because, as you can see, the lengths in SI, the length is in meters, displacement in millimeters, but then the area in millimeters square, but then the distributed load is in kilonewton per meter. So the units kind of make sense because, sections usually are in millimeters and lengths are in meters, but they're not consistent. So the best way to get this to work straight away without any problems is to press here kilonewton meter, and here you can read the message all units in kilonewton and meter, which makes sure that all the units are consistent. So everything is in meters and everything is in kilonewtons. So now I'm going to press OK. And now what's the advantage? If I start a new material model, which I can do here, and I'm going to call it something, I can set up my E to be exactly 1 kilonewton per square meter. So then I press all, and I make sure that every single material in this bar, so the entire bar, has a material properties of 1. In this case is 1 kilopascal, which is the same as kilonewton per square meter. So now I can go to the section properties, and I'm going to do the same trick, but now I'm going to turn on this integral properties in F-tool, which is the menu that allows me to set up any number I want for the section properties. And the one I'm interested in is I. I want I to be 1 meter to the power of 4. So now I can press all, and then after I set up all my structure, I should be able to verify very quickly this equation, because I know that E is 1 and I is 1. So then I can just take this part of the equation here, and then I can make sure everything is working fine. So let's continue. So the rest of the structure is a pin support in one of the sides, and then a roller in the other side. So it should look like this. Then I'll get some loads. So I'm not sure which load is this. So let's go here, scroll back up. That's 30. The other one is 24. So let's put minus 30 here. Let's put here 24. So I need to create another load. Make it minus 24. Then I have a moment of 6 here. So let's start a new load. Moment of 6. And apply. Let me just confirm this is the right direction, which is not, so I need to put minus 6. Okay, and now for the UDL, I need to go to this menu here, the one for uniform loads, and then apply a load of minus 24. So QY minus 24, and off we go. Okay, so my structure is there, my material properties are there, section properties are there, so then I can go straight away and get axial deformation. Okay, so what F-tool is telling me is that I need to have at least a value for the area. So I'm going to put 1 for the area and apply to all. Now I should be able to run it. Okay, so now it's good. I'm just going to save it here. And here is my deflection. So this equation that you see here basically describes this deflection here. So let's see, for example, what would be the displacement at z equals 3. So if I go here to z equals 3, I can right click and I can measure that the displacement will be minus 285.5. So F2 is telling me that this is 285.5 times 10 to the 2. If you want to see it in a different way, we can go to units and formatting and change the displacement not to have the exponential, not to have the scientific notation. So then we should be able to read it straight away. So minus 285.5, which this should be the value of the displacement when z equals 3. So now if I continue my problem and I replace when z equals 3, I'm going to get 1 over ei. That's just going to be 1. But for now, let's write it down. And here we're going to get minus 10 times 3 cubed plus 5 times 2 cubed plus, and here should be 2 to the 4. Here should be minus 0. And from this point onwards, because these values are going to go to negative, all of this goes to 0. And at the end, we get a plus 333 over 2 times 3. So now if we put this in the calculator, the answer we get is 285.5. So in this case, 285.5 should be in millimeters because we're talking about the displacement, and it's downwards according to the assumptions that we followed. So if you go to F-tool now, we can see that very well, we got our 285.5, but this comes with a minus sign, which just basically means that F-tool does not carry the assumption that the curvatures are equal to the minus moment divided by EI. So in F-tool, this minus sign is not taken into consideration. It's kept positive, which that means your deflection comes with a minus sign, but has the same meaning. Another thing we can check is the rotation when z equals 0. By definition, the rotation when z equals 0 is the value of c. So here should give me 333 over 2, which is 166.5. So if you look at the equation of the rotations, you can see that if you replace, so the equation of rotation is this one here. If you replace z with 0, you get that the rotation is just c divided by ei. But as you know, today we are assuming ei to be 1. So we should be able to measure this rotation straight away in F-tool. So 166.5, let's just go very quickly to F-tool. Right click here at z equals 0. And here we get our minus 166.5. Again, the minus sign just has to do with the assumptions of F-tool. So I hope you enjoyed the video. The only trick here is to make sure your units are consistent and then making sure your E and your I are equal to 1. And then you can read straight away the values of the displacements. If you get a real section with a real material, you could just replace and get the correct values. So let's say it would be steel. So the E of steel would be 210 gigapascal, which should be around 210,000 megapascal. And megapascal have the same units as Newton per millimeter square. So that's one option you could do this. Another option could be 210 times 10 to the 6 kilopascal. And this will give you the units of kilonewton per square meter. Okay? And then your I, let's say if you have a square section, it's just bh cubed over 12, being b the base of your section and h the height of your section. So all of these things can be calculated. So you just need to be careful with your units so that you make sure that at the end you get the right answer. So I'm going to flip this back up. Thank you for watching and have a nice day.